In this section, we are going to plot the AC small signal equivalent circuit for the DCM converters. And utilizing this equivalent circuit model, we can derive its transfer function. So small signal transfer function. So previously, we have obtained the mathematical model for the switch network with first order AC terms, right? Now I released those three conclusions. First is I1 small signal equals to V1 times 1 over R1 plus V2 times G1 plus small signal duty cycle times J1. And for the output port, the small signal AC current equals to V2 times -1 over R2 plus V1 G2 plus D J2. So this pair of equations can be represented by a equivalent circuit, actually. So for example, the input port function can be denoted as such a equivalent circuit. So here is the I1, and here is V1. So this part is a resistor behavior, right? Resistance is R1. This part is a controlled current source behavior. The expression is J1 V2. V2 is the output port voltage. And this part is a independent current source behavior. So you will see that this circuit is equivalent to this function. Similarly, we can also plot an equivalent circuit for the output port. So this one is also a controlled current source behavior. So which is G2 V1. And we denote that this is the V2. And this current is I2, right? So this branch contains a controlled current source term, which represent this one. And this one will be another independent current source. And third one will be a resistor, right, whose resistance is R2. So there is minor sign here. That's why the polarity of the output port is inverted. Here is positive. And next, let's try to utilize this equivalent circuit into a specific pulse width modulated converter in DCM. So we consider the buck boost example here. So in retrospect, let's plot the buck boost converter here. So this is the buck boost, right? L, C, resistance, and the input voltage is here. Output voltage. So we can extract a switch network here and denote the polarities of voltage and currents. So here is the V1, and this is I1, and this is V2, and this current is I2. So the next step, we can replace this switch network, the two-port network, by its equivalent AC model here we just derived. So actually this, we just insert into here, right? And replace those quantities by their small signal AC parts. So this one is going to be the VG cap. And this port is replaced by this one, right? I use a blue chalk to show you that I'm basically copying here. R1, J1D, G1, V2. And this is I1 small signal. And this voltage is V1 small signal. So the input port and output port, they have a common point here, right? Then the output port is replaced by this network. So here is the R2. Here is the J2 D cap. And this one is G2 V1 cap. So the polarity here is positive on bottom, right? V2. And current direction is here, I2. So I use the red chalk to make up the rest part. Here there is a inductor L, C, R. So this is the small signal output voltage. So till now we have derived the small signal AC model for buck boost topology in DCM. Okay, then we can analyze this equivalent circuit model. Based on it, we can derive the transfer functions, right? So for DCM operation, usually the inductance is pretty small, right? So that the ripple current is large, we can enable DCM operation. So L is small. In DCM. So for simplified analysis, we can consider L as short circuit. At low frequency. this is only approximated analysis. Later on, we are going to provide the precise analysis. So if L is considered as a short circuit at low frequency, right, meaning that we can replace L by a wire, meaning a short circuit. So based on the simplified model, we can try to derive its transfer functions accordingly. So first one we care about is the control to output. So we use GVD to denote in S domain, right? So GVD is defined as the ratio between output voltage, small signal, and the controlling signal, D, in the condition that the line input small signal is 0. Now let's look at this circuit. So if the line input is 0, then on the output port, this one will be equals to 0, because VG equals to V1. Here is short circuit, right? VG, based on KVL, VG equals to V1. And this quantity is V1 times G2. So this current source will be equal to 0. So for current source equals to 0 means that it's open circuit, right? Open circuit. Then we'll see that the output voltage will only be determined by this excitation source. So this current is J2D cap, right? So this current source feed current to the parallel of R2, C, and R, so that the output voltage can be easily solved as in the numerator, which will be this current times the impedance of the parallel of R2, R, and C. So current J2D times the impedance of R parallel with R2 parallel with C, whose impedance is 1 over SC in S domain. Denominator is still D cap, right? So interesting thing is that we can find that the D cap are cancelled on the top and the bottom side, so that the result will just be J2 times this parallel impedance. We can normalize this transfer function. So normalize it will be a single pole response, because there is only one S term here. This impedance will be a single pole response. So we can normalize it to be decibels divided by the single pole response. And by comparing this and this expression, we can write the expressions for decibels, right? GD0. For DC, actually, the capacitor can be treated as open circuit. So meaning that it's only the parallel of R and R2. So this GD0 will be equal to J2 times R parallel with R2. Omega P is determined by the time constant of C and this parallel R, right? So 1 over time constant, which is R parallel with R2 times C. So that's it, right? That's it. Pretty simple and straightforward. And the next transfer function we care about is the line to output transfer function. we denote this transfer function as GVG. So this time, this is no longer open circuit. Okay, GVG as its definition is that the ratio between output voltage and line input, small signal, under the condition that the controlling input is 0. For this time, if the controlling input is 0, meaning that this one, J2D, will be equal to 0. So the current equals 0 means that this can be treated as open circuit, so that the output voltage is only determined by this current, which is controlled by the input voltage V1, and V1 equals to Vg. Right? So therefore, we can also easily list the expression for output voltage in the numerator, right? Which is G2 V1 equals to G2 Vg. Right? So this current times the parallel of R2, C, and R. Divided by the line input. So this is because Vg equals to V1. Okay. So again, the Vg part is cancelled. Right? So this result will be similar to this one. Only difference is the coefficient G2, right? Coefficient G2. So you can imagine that the normalized transfer function will be the similar format. So GG0 over 1 plus S over omega p, which is also a single pole response. So the DC bias GG0 will be similar to this one, but we replace J2 by G2. Omega p will be identical, right? Equals to 1 over time constant. So that's the complete transfer function set with the approximation that L is small in DCM and can be ignored. So in this section, we have plotted the AC small signal model for DCM buck boost converter. And utilizing this small signal model, we can derive its control to output and also line to output transfer functions.